picture this. You've audited your code. There are no open files, no slice leaks.
Right, the usual suspects are clean.
Exactly. Your defer calls are rock solid. Your garbage collector's running perfectly. And yet, your server is bleeding 50 megabytes an hour.
Which is terrifying.
It is. You are slowly but surely heading for a total application crash. So, welcome to today's deep dive.
Yeah, today we're looking at a memory leak that actually has absolutely nothing to do with memory.
Right. We are unpacking an article by Aaron Rose. It's from tech-reader.blog, and it's called The Secret Life of Go, Goroutine Leaks.
And our mission here is to really dissect this silent, invisible architectural flaw that, takes down distributed systems every single day.
It really does. And Aaron uses this great narrative to explain it, focusing on two engineers, Ethan, who's a junior engineer, and his senior colleague, Eleanor.
I love the setting he uses for this, too. He places the story in this quiet, beautiful Beaux-Arts library in Lower Manhattan.
Which is so unusual for a tech story. Usually we're in a messy open-plan office.
Right, or a noisy server room. But the library setting is so deliberate, it really highlights the core theme of the whole piece, which is the management of finite resources.
Because shelf space is limited.
Exactly. Whether it's physical shelf space or digital memory, you just can't endlessly consume without returning what you take.
And that limited space is exactly what Ethan is running out of. He's slumped in his chair, staring at a Grafana monitoring dashboard.
Looking at a graph that is basically a developer's worst nightmare.
Yeah, it's not spiking. Like spikes in traffic are normal. You can scale for an event. But Ethan is staring at this slow, relentless, 45-degree angle upward in memory usage.
Which, is the universal visual shorthand for a system death spiral.
Oh, wow, really?
Oh, absolutely. A steady upward slope means you have a structural flaw. Somewhere, memory is being claimed and just never released.
And servers only have so much RAM.
Right. If that line goes on long enough, it hits the ceiling, and the operating system's out-of-memory killer just steps in and terminates the application.
Just pulls the plug to protect the rest of the server.
Exactly.
So Ethan knows this, and he's done all this exhaustive troubleshooting. He checks for slice leaks, open files, everything is clean.
Because he's looking at the symptom, right, the disappearing memory. He's trying to find the data that's eating it.
But then Eleanor steps in and takes a completely different approach. She ignores the memory graph entirely.
Yeah, she checks the thread count instead.
Right. And the dashboard shows active Goroutines sitting at 4,200.
Which is a massive reveal. She basically tells him, the ghost isn't in your data, it's in your workforce.
Which changes everything. So let's talk about the business logic that actually caused this.
Right.
Because Ethan was doing something really common, right?
He was. For every incoming request, he needed to fetch metadata from this notoriously slow legacy API.
So to keep his main service fast, he runs a background check. He launches a Goroutine to fetch the data.
And if it takes too long, the main request just times out, sends a response to the user, and moved on.
He thought it was just a standard fire and forget maneuver. But wait, let's unpack this for a second.
Okay.
Doesn't modern programming have automatic cleanup? Like, shouldn't a built-in garbage collector just sweep away these forgotten background tasks once the main request moves on?
You would think so, but no. That's a huge misconception, especially in Go.
Really? So the garbage collector just ignores them?
Well, it's about what the garbage collector actually manages. It manages the memory heap, not the execution stack.
Oh, okay.
The unbending rule of the Go runtime is that Goroutines are not garbage collected until they actually exit.
Wait, so as long as a worker's trying to do something, the system thinks it's still alive?
Exactly. Even if it's just paused or waiting on a channel, the runtime considers it an active root reference.
But why design it that way? Why not just kill the thread if the main request is done?
Because of data corruption. Imagine if that background worker was halfway through writing a record to a database.
Oh, right.
Or holding a critical mutex lock. If the runtime just assassinates that thread, your entire database could deadlock.
Wow. So the system has to assume the worker's doing something important until the worker says it's finished.
Precisely. Which means Ethan's background tasks aren't dead. They are trapped in this state of suspended animation.
All 4,200 of them.
Yep. Zombie workers.
So what are these zombies actually doing? They can't just be floating in a void.
Well, they eventually get the data from that slow legacy API. And their final instruction is to send that result back to the main program.
Over a channel, right. The code specifically shows them using an unbuffered channel called sheech.
Right. And that unbuffered channel is the fatal bottleneck here.
Because unbuffered means Both sides have to be ready at the exact same time.
Exactly. It requires strict synchronization. A sender and a receiver have to meet. It's a blocking handoff.
But the main request already timed out. The user went home.
So there's no listening thread on the other end.
And because it's unbuffered, the worker just halts. It blocks forever.
Forever. And this is where the physical cost of a logical error comes in. You're still paying for all those blocked processes.
Okay, I have an analogy for this. Tell me if this works.
Let's hear it.
It's like sending a dedicated intern down into the basement archives to fetch a specific file.
Okay, I like where this is going.
They go down, find the file, but while they're down there, you leave for the day and lock the basement door.
Ah, that's brutal.
Right. But the intern doesn't just cease to exist. They stand there forever holding the file, just waiting for you to open the door.
That is a perfect analogy. And it ties right back to Eleanor's library setting. Just like physical space in a library is finite, digital space requires stewardship.
Because every intern in the basement is taking up space.
Exactly. Every blocked Goroutine holds on to its localized variables, the network buffers, the parsed JSON. It's all sitting on the heap.
Dragging the server's memory capacity into the abyss.
Yeah, 50 megabytes an hour, like we said.
So how do we rescue the intern? How do we stop the zombie apocalypse in the code?
Well, Eleanor introduces what she calls the architect's rule.
Which
Never start a Goroutine without knowing exactly how it will stop. You have to take full life cycle responsibility.
Okay, so she gives Ethan a two-part solution. The first part is implementing a tether.
Right, using the context package.
That's the standard way in. Go to signal cancellation and timeouts across API boundaries, right?
Yes. It lets a parent function definitively tell its children that their work isn't needed anymore. It's like a cascading power cut in a building.
Oh, I like that. So when the main request times out, it flips the main breaker.
Exactly. It shuts off power to the HTTP request, forces operations to return an error immediately, and cuts the wait time.
But wait, let's look at the state machine here. What if the worker already got the payload? The network call is finished. So the cascading power cut doesn't magically open the basement door, does it? The worker is still holding the data, trying to send it on the channel.
You've hit the exact edge case. Context cancellation alone is not enough. The Goroutine is totally blind to the cancellation at that specific microsecond.
It's locked in the channel send operation.
Right. Which brings us to part 2 of Eleanor's solution. She changes the channel infrastructure.
She turns it from an unbuffered channel into a buffered channel of size 1.
Yes.
Now, I have a question about this. Are we just giving the worker a Dropbox to leave the file? Like, we know the API is slow. Shouldn't we use a circuit breaker pattern to stop sending workers in the first place?
That's a great systems design question. A circuit breaker would definitely protect the legacy API from being hammered.
Right. If it's failing, just trip the breaker.
But Eleanor isn't addressing the load. She's addressing the leak. Even with a circuit breaker, the requests that do go through still need an exit strategy.
Okay, so break that down for me. How does adding a buffer actually allow the worker to escape?
Because a buffered channel decouples the sender from the receiver. It introduces an intermediate QA Dropbox.
Of size 1.
Right. So when the worker returns with the metadata, it initiates the send. Because the buffer is empty, the send operation succeeds immediately.
Oh, wow. So it just drops the payload in the box and leaves.
Exactly. It no longer cares if the receiver is actively listening. The function reaches its natural conclusion and the Goroutine gracefully exits.
And the ghost is laid to rest.
Yes. And once the Goroutine exits, the runtime doesn't see it as an active root reference anymore.
Which means the garbage collector finally has jurisdiction.
Right. The next time it runs, it sees the stack is gone, sweeps the entire structure away, and reclaims the heap memory. Plugged leak.
That is so satisfying. You're working in harmony with the runtime instead of fighting it.
Exactly.
So Aaron Rose describes the aftermath of this fix. Ethan deploys the refactored service, and it's basically the return of the shelf space.
Yeah, though it's important to note the memory graph doesn't just go flat.
Right, a flat line means a dead system. When traffic hits, memory still spikes, and the active Goroutines surge.
Because the system is doing work. The critical difference is the recovery. As soon as the load drops, the lines plummet back to baseline.
The system breathes.
Yes, it expands and contracts naturally. The 45-degree angle of doom is gone.
Which brings us back to Eleanor's library. In a library, an unreturned book deprives the rest of the ecosystem.
And in Go, an unreturned execution thread is a structural fracture. You can't just fire and forget.
Workers always have to know the way home.
Absolutely. The fire and forget fallacy is a huge trap.
And I think that applies outside of software engineering too.
Oh, definitely.
Think about the workflows or personal projects you initiate in your own life.
Hmm.
Where might you be operating with a fire-and-forget mentality?
That's a really good question.
Right. Are you leaving metaphorical zombie workers behind, like unresolved tasks or ambiguous delegations, just because you haven't built in a tether or an exit strategy for when things don't go according to plan?
It's so easy to just assume things will resolve themselves.
Exactly. It's something to seriously consider. Whether you're writing back-end code or just managing a project, you have to architect the ending before you initiate the start.
Always know how it stops.
Always know how it stops. Thanks for joining us on this deep dive, and we'll catch you next time.